So our topic yesterday from section 11.1 dealt with counting ways things can happen, right? How many outfits can we make? How many license plates can we make? How many different arrangements can we make with file folders, putting them in a drawer, things like that. We also talked about not using all items, like there's 10 runners and we only are concerned with the first 3 place winners, okay? So it was just focusing on counting ways things can happen. That was going to come back tomorrow when we start talking about using NPR and NCR, things like that, for actually calculating probability. Today we're just going to introduce the topic of probability and the different types of probability that we can calculate. So our focus today is looking at theoretical and experimental probability. We're also going to do a simulation with your graphing calculators to simulate an experimental probability situation. Okay? All right, so the probability of an impossible event. Impossible means it can't happen. So what is the probability at the end of the semester you get your report card and your grade for Algebra 2 is an H? Can I give you a grade of an H? Is that one of the letter grades we use? No. So what is the probability of that? 0, right? Can't happen. So for an impossible event, our probability is 0 or 0%. The probability for a certain event. What is the probability at the end of the semester you get your report card and you have a grade for Algebra 2? What is it going to be? 100%. Yes? I'm going to give you a grade. So we can either say that is a probability of 1 or we can say 100%. So probabilities are going to be numbers somewhere between 0 and 1 if we list it as just a regular number or fraction, or if we put it in percent format, between 0 and 100%. Okay? So our first topic here is experimental probability. To calculate the probability of some event, with experimental probability, we take the number of times the event occurs compared to the number of trials. So the idea with experimental probability is this is what does happen. This is what actually happened. We are going to use data. Either we collected it in a survey or using an observation technique or some kind of experiment. We've got some data to use. Okay? So this is what actually happens. And we, again, take that data either from observations, experiments, simulations, something like that. Our first example says, of the 60 vehicles in a teacher's parking lot today, 15 of them are pickup trucks. What is the experimental probability? So again, based on the data, what is the probability that a vehicle in the lot is a pickup truck? So to calculate this, we're going to say probability that we have a truck. What would we need for the top number? Just in words, not numbers. What are we looking for? Okay, so number of trucks compared to total number of vehicles. So how many trucks did we have? 15 out of 60. Can we reduce that fraction? 1 out of 4? Yes, 15 goes into 64 times. 1/4 would be the same as what decimal? Okay. And 0.25 is the same as what percent? So, do we have a number between 0 and 1? Yes, doesn't matter if you write it as 1/4 or you write it as 0.25. It's still a number between 0 and 1. Is our percent between 0 and 100%? Yes. Okay. Go ahead and do the second question here. what is the probability of getting a hit the next time she's at bat if our data says that she got a hit 20 times in her last 50 at-bats? What's the probability? As a fraction, what would we put? 20 over 50, okay. That does reduce to 2/5, which would be 0.4, which is 40%. Now, do you always have to put all those different forms down? No. If it specifically asks for one version, obviously I want you to give me that. But if it's up to you, you can put it as a fraction, decimal, or percent. I don't care. Questions on experimental probability? Okay, we're just basing it on the data. Sometimes actual trials are difficult or unreasonable to conduct. In these situations, we can estimate the experimental probability of an event using a simulation, which would be a model of the event. Okay, a simulation. So this is where you need your graphing calculators. Go ahead and get those out. I have some on my desk if you need them. All right, so our example says, on a multiple choice test, each item has 4 choices, so A, B, C, D, but only one choice is correct. That means for question 1, I can't put down both A and B and expect both of them to be right. Okay? How can you simulate guessing the answers? What is the probability that you will pass the test by guessing at least 6 of the 10 answers correctly? So there's a couple things you need to pick out from this. How many questions are on the test? 10. They said they wanted 6 out of 10 right, correct? So we have 10 questions on the test. How many answer choices do we have for each of those questions? How many? 4. Okay. All right, 4 choices for each question. But again, for each question, only one is correct. Yes? What we are going to do is have our calculator pretend to answer those 10 questions. Okay? Your graphing calculators can generate integers randomly. So what we are going to do, we are going to go to our math key, scroll over to probability, and then you are going to choose random integer. Okay, so the math key, probability, and then random integer. Math, oops, probability, and in mine it's number 5. Now, the newer calculators are going to have this screen for you. Older calculators, it should just say random integer with a parenthesis. Okay, so what you're going to put in there we are going to look at the answer choices. We said we had 4, right? A, B, C, D. So we wanted to generate a number between 1 and 4 to represent the different answers that could be given. Calculators aren't going to generate your letters, so instead of A, B, C, D, we're going to do 1, 2, 3, 4. So you are going to put down 1, 4. If you have the newer screen, then lower would be 1, upper would be 4. Okay? Then we do a comma, or on the newer screen it goes down to n. And now we tell it how many questions were on the test. So we had 10 questions. So what it's going to do for us when we hit enter is it's going to give us a list of 10 numbers between 1 and 4. Okay? Now, On some calculators, you're going to have a little arrow key at the end of that list of numbers, and it has dot, dot, dot. That means there's more of them that you just aren't seeing. Before you hit any other key, use your right arrow, and you can scroll through that list. Okay? What this has done now is it has selected an answer choice for each of my 10 questions. So it's pretending it's taken the test one time. Okay? If you were going to do this on your own, if it was a homework question, you would go through and do this 20 times. Now, you can just keep hitting enter and it'll keep repeating it, but giving you a new list of 10 numbers. Okay? We are going to save some time. So, at your table, you have 2 whiteboards. 2 of you grab a whiteboard and write down the numbers that you had on your calculator, your list of 10 numbers. All right, so once again, we have 20 whiteboards sitting out here. Yes, each one has a list of 10 numbers. The trick to doing this is you are going to randomly choose one of the 4 numbers, 1, 2, 3, or 4, to represent the correct answer. Okay? So, for this example, I'm going to choose a 1 to equal a correct response. So if I look at my list that I generated, okay, I have a 1 there and a 1 there. So question 1, 2, 3, 4, and 5 I all got wrong. Question 6 I got correct. 7 and 8 were wrong. 9 was correct and 10 was wrong. Does that make sense? How we interpret that? Okay, so you can't pick it based on the numbers you got, right? You randomly, before you hit enter, you randomly say, I'm going to have 1s be my correct response. I only got 2 right. So 2 out of the 10 questions I got correct. What it's asking me here is, what is the probability that I got 6 of the 10, at least 6 of the 10 correct? So look at your boards. I want you to count up how many 1s you have on your list. Did anyone have 6 or more 1s? Okay, so for this experiment, the probability of getting 6 or more correct ends up being 0 out of the 20 trials that we did. Yes? Does that mean that my probability of getting 6 or more right is 0? It means that based on my simulation, in the 20 trials I did, none of them worked. What if I did 200 trials? Am I likely to get a few that might be 6 or more? Yes. Okay. For our cases, 20 trials will be plenty. We'll base our answer off of that data. Okay? What if we changed it now? The second question here asked for 5 out of 10. What is the probability of score of 50% or better? So we need 5 or more. Did anybody have 5 or more correct? Meaning 5 or more 1s. Anybody? Okay, so we still were at 0. What about the probability of 4 or more? How many got 4? 4 1s. 1, 2, 3, 4, 5. All right. So our probability was 5 out of 20, or 1/4, or 25% probability of getting 4 out of the 10 correct. Does that make sense? So it's a way to simulate an experiment without actually taking that test 20 times. Does that make sense? So, question for you. What if we had 15 questions on our test, and we had 5 answer choices possible? How would we set that up? we would do random integer, and then what? What numbers would I put in? How many choices do I have? 5. So I want it to generate numbers between 1 and 5? Yes? Okay, so 1, 5, and then what's my last number going to be? 15. All right, 15 questions. So I could do that. And again, if this was my homework question, I would have to generate 20 trials all by myself. The most common thing is students forget how many they've done. Okay? So what I would do, if this was asking me for the probability of, say, 5 or more correct, representing passing, I would just make a tally chart. So I generate the first list of 15 numbers. I count, how many ones do I have? If I have 5 ones or more, I'm going to put a tally there. If I don't have at least 5 ones, I'd put a tally in the fail column. And as soon as you get 20 tallies, you know you have all your data. Does that make sense? Okay. Questions on using the random integer feature of your calculator? All right. So that's all for experimental probability. Switching to theoretical probability. It says the set of all possible outcomes to an experiment or activity is the sample space. When each outcome in a sample space has the same chance of occurring, we refer to those outcomes as equally likely. So for theoretical probability, it says if a sample space has n equally likely outcomes and an event A occurs in m of those outcomes, then the theoretical probability of event A happening is m divided by n. So instead of basing it on data like we did with the pickup trucks, this is what should happen. Okay? Not what did happen, but this is what should. Theoretically, what should occur. So I will give you an example. I have a coin. How many outcomes do I have when I toss a coin? 2, heads and tails, yes? So my sample space would be heads and tails. If I wanted the theoretical probability of tossing a coin and getting tails, what would I say? What's the theoretical? What should happen when I toss a coin? 50% chance, yes? I have 2 outcomes, they're equally likely. I have a 50% chance of getting heads and I have a 50% chance of getting tails. If I toss a coin 10 times, I've done an experiment, okay? Let's say I toss a coin 10 times and 4 times I get heads and 6 times I get tails. What did I say? Heads was 4, tails was 6. What is the experimental probability of getting tails? How many tails did I get? 6 out of how many trials? 10? 6 out of 10 would be 60%. Theoretically, I should have gotten 50%. Experimentally, I ended up with 60%. Do you see the difference? What would happen if I tossed the coin 1,000 times? Do you think I'd get closer to that 50-50? Yes. The more experimental trials you do, the closer to the theoretical you get. Okay? All right. So in this example, it says, what is the theoretical probability of getting a 5 on one roll of a standard number cube? So we're rolling a die. We're just rolling it one time. What is the sample space? When you do the sample space, you actually list the outcomes. What are the outcomes that could happen? All right, the numbers 1 through 6. Yes? Now, what is the probability that I get a 5? Well, in that one roll, I had the choices 1 through 6. I want it to come up a 5. How many times does it come up a 5? How many chances? 1 out of the 6 outcomes that could happen. So the probability of getting a 5 is 1 out of 6. Does that make sense? What is the probability of getting a number greater than 4? Now which ones work? What can I roll that would get me a number greater than 4? 5 or 6. So I have now 2 outcomes out of the 6 possible ones. So I have a 2 out of 6 chance, or 1/3 chance of getting a number greater than 4. Does that make sense? All right. Our next chart is assuming that we toss the coin, that we roll the die, roll 2 dice. Okay? We're just rolling them once, but we roll 2 dice. Okay? So, on the left side here, we have die number 1. Our options are 1, 2, 3, 4, 5, or 6. On the top, the second die, same thing. We can get a 1 through 6. What you have inside here is the sum. So if I roll 2 1s, they add up to 2. If I roll, say, a 4 and a 3, that gets me a 7. Does that make sense? What the chart lists? All right. So now it's asking, what is the probability of getting a sum of 5? So I look at my chart. I've got a 5 there, 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 and there. How many outcomes is that? How many did I circle? 4 of them. So I have a chance 4 out of, how many different outcomes are listed in that chart? It's a 6 by 6 grid, yes? So I have 36 outcomes total. So I have a 1 out of 9 chance of getting a sum of 5. Agree? Okay. What is the theoretical probability of getting a sum that is an odd number? Go ahead and figure out how many options you have that sums would be odd. How many did you come up with? 18 out of 36? So what is that probability? 1836 is the same as 1/2, or 50%. So I have a 50% chance of getting a sum that's odd, which means I also have a 50% chance of getting a sum that is even. Okay? All right, last question. Without calculating the probability, is it more likely to get an even or odd number on one roll of 1 die? Okay? I roll 1 die. Is it more likely to get an even or an odd number? Is it a trick question? Why? They're equally likely, right? I had 3 evens and 3 odds. Okay, so they are equally likely. All right. questions on experimental probability and theoretical probability? All right. Tomorrow we will start looking at geometric probability, which is just using a geometric concept like area or length, volume, to help predict something. And then also looking at using permutations and combinations to help us calculate probabilities. All right, so your assignment is listed there. Let me know if you have any questions.